let's say I have a tree, and let's say I just add one new edge to my tree. I claim that this creates exactly one cycle. So adding an edge E to a tree T creates exactly one cycle. So to visualize this, just imagine that I have a tree. This is my original tree. Let's call it T. And then I'm adding just one new edge. Let's call this one E. And I say that when I look at T plus E, it's going to have a cycle, and it's going to have exactly one cycle. Okay. First of all, why would it have a cycle? Because T already had n minus 1 edges. So I'm adding this new vertex. Sorry, I'm adding this new edge. And now I have n edges, right? But if it doesn't have a cycle, since it was already connected, it should remain a tree. But if it remains a tree, it should have still n minus 1 edges, which is not the case. I have n edges, right? Or another way of looking at this is the same argument that we made when we were adding the edges one by one to a graph. So before adding the edge E, my graph is connected. It's a tree. So these two endpoints are going to be in the same connected component, which means that there is already a path between these two endpoints. So when I add the edge E, this new edge with the path that already existed between the endpoints is going to create a cycle. So I'm definitely going to get a cycle. But why do I get exactly one cycle? Why is it not possible to get two cycles, for example? Or maybe even more. Who knows? Maybe I add an edge, I get 10 new cycles.
There are only one edge from that point.
Yes. So I know that before adding E, I didn't have any cycles because before adding E, it was a tree, right? So any new cycle that is created has to contain the edge E. Now, just imagine that there are more than one cycles. There are, let's say, two cycles that contain the edge E. So this is the edge E. And let's say there are two cycles that contain it. So there is this cycle, and then there is also this cycle. But if I just put the red sides together, I will get a cycle in my original graph, which is a contradiction because my original graph was supposed to be a tree, right? So if I have a tree and I add one edge, I get exactly one cycle. Okay. Now I want to move to something else. One thing that we do very often is that we give weights to the edges in our graphs. So a weighted graph is this. It's basically a set of vertices, a set of edges, and a weight function. Okay. So it consists of the same things that we had in a normal graph. So GVE, which is a graph. And I'm doing a slight abuse of notation here because I'm using G to represent VE, but also VEW, right? And I also have a function W, which takes edges and maps them, let's say, to real numbers. Okay. So basically, whenever I talk of a weighted graph, imagine that I have a graph, but I also have some weights over the edges. Okay. And these weights don't have to be positive. Maybe I have a negative weight as well. Now, in this kind of graph, a lot of the problems that we have already solved will be very different. So we've talked, for example, about shortest path. And when we were talking about shortest path, we were saying that if I want to find the shortest path from U to V, that's the path with the fewest number of edges. But now this is not necessarily the case. because I'm thinking of these weights as the lengths of this path. So I can take this path, for example. Let's say this is my vertex U, and this is my vertex V. I can take this path, and it has, let's say, a cost or a weight of 2. But I can alternatively take this one, and it has a cost or a weight of -1. So this one is cheaper. So when in a weighted graph, I talk about the shortest path, I'm talking about the cheapest path. And also, it's not necessarily even a path. So sometimes we talk about shortest path, but we actually mean shortest walk. Okay. So I want you to remember one thing that we talked about before, and this was this notion of a spanning tree. So we said that every graph G, which has some vertex set V and edge set E, contains a subgraph. Let's call this one T, on the same set of vertices, but of course with a different set of edges, such that T is a tree. Right? We've already proven that this exists. And we said that we call this T a spanning tree. Sorry, this was every connected graph. Okay. So if I have a connected graph, I can always find a subtree in it. I can always find a subgraph that is a tree. Okay. And the proof was, again, very easy. It was this idea that I keep adding edges one by one, and I don't add edges that create cycles. But now I want to talk about a very particular problem, and this is the problem of minimum spanning tree. Because you see, now I have weights or costs associated to the edges. And so I can say, what is the spanning tree that has the smallest overall cost? Okay. So given a weighted graph, a subtree of this graph, so a subtree T of G, is an MST. MST stands for minimum spanning tree. If, well, of course, it's a spanning tree, and also it has the smallest total weight among all spanning trees. If it is a spanning tree with the least total weight. Now, why is this useful? So I'm just going to give you one example. Imagine that we have a bunch of cities again. As usual, we're thinking of our vertices as cities. And let's say that there are a bunch of roads that we can or cannot construct. I don't know if I want to construct each road or not, but let's say I have a bunch of roads that I can construct, and I show them with the edges of my graph. So if I don't have an edge between a pair of vertices, it means that I cannot construct a road between them. And if I do have an edge, it means that I can construct a road. And let's say that I have a cost associated to each of these roads. So for example, constructing this road would take 2 units of money. Constructing this one would take 5. This is 10. This is 2 again. This is 1. This is 3. This is 6. Okay. So my question is, what is the minimum cost to connect every node to every other node? So that's going to be a minimum spanning tree, right? Because of course, if my goal is to just connect all of my cities, all of my nodes here, I will not create a cycle. I will just create a tree, because what's the point of creating extra edges and paying for them, right? But among the trees that I can make, of course, it has to be a spanning tree. It has to touch every vertex. It has to connect everything to everything. But I also want to pay the least amount of money overall. Okay. So this is the minimum spanning tree problem. Great. Give me an algorithm. How would you find the minimum spanning tree? If I give you a graph, how would you find the minimum spanning tree? So here's a very easy algorithm. This is Kruskal's algorithm. And when I explain it to you, you wouldn't even believe that this works. But basically what it says is sort all the edges by their weights from the cheapest edge to the most expensive. And start going over these edges. And every time check if this cheapest edge creates a cycle. If it doesn't create a cycle, take it into your minimum spanning tree. If it creates a cycle, don't take it. So in this case, I can sort my edge weights, and I have one edge of weight 1, 2 edges of weight 2. And by the way, if the weights are the same, I can put them in any order. I don't really care. Then I have 3, 5, 6, and 10. So I first look at my edge of weight 1, or my road of cost 1. And I say, if I construct this one, will it create a cycle? No. So I will construct it. So I show what I'm constructing in blue. Okay. Then I look at one of the edges with weight 2. Again, I'm just going in the order of increasing weight. And I ask, does this create a cycle? No, it doesn't create a cycle. So I construct it. Then I go to this other edge of weight 2. Does this create a cycle? No, it doesn't. So I construct this. I look at my edge of weight 3. If I add this edge, would it create a cycle? Yes, because I've already created 1 and 2. So I ignore this one. I go to the next edge, the one with weight 5. I see that I can construct it and it doesn't create a cycle. Then I go to the edge of weight 6. I see that constructing it will create a cycle, so I don't construct it. I look at the edge with weight 10. I see that adding this one will also create a cycle, so I don't add it. So this is giving me a spanning tree. And what is the total weight? The total weight is 1 plus 2 plus 2 plus 5, which is hopefully 10. And the claim is that this is a minimum spanning tree. So the claim is that what this algorithm does is always outputs one of the minimum spanning trees. Again, my minimum spanning tree might not be unique. Maybe I have 2 different minimum spanning trees or many different minimum spanning trees. Actually, one interesting question would be, what is the maximum number of minimum spanning trees you can have? But in any case, it's not unique, but this algorithm finds one of the solutions. It finds one of the minimum spanning trees. Okay, so this is the algorithm. Again, sort the edges by weight in an increasing order. And then add an edge if it does not create a cycle. So of course, in this order. Okay. We want to prove that this algorithm is correct. We want to prove that this algorithm produces a minimum spanning tree. Now, for your algorithms, whenever you're talking about correctness, the first thing you have to prove is that the algorithm terminates, that it doesn't run forever. But that part is quite easy because, of course, sorting terminates, and then I'm going over every edge once. So this algorithm cannot run forever. It will terminate. Okay. Now, I want to prove that what it produces is a spanning tree. We will come back and talk about it being minimum afterwards. But why does this algorithm produce a spanning tree? Yes, it checks every edge. So it keeps adding some edges. We know that it doesn't add a cycle, right? Because that's in the algorithm. Every time it wants to add an edge, it checks whether this edge creates a cycle. So, and it only adds it if it doesn't create a cycle. So this algorithm will definitely not cause us to have a cycle. So all I have to say is that these blue edges, the edges that the algorithm adds, actually create a connected subgraph. Because if it's connected and it doesn't have a cycle, it's a tree. Right? So why does the algorithm connect everything to everything? So this is my first point. I want to say that the output is connected. And of course, this is assuming that my input was already connected, right? So I always forget this. Given a connected weighted graph, because if it's not connected, it doesn't have a spanning tree, right? Okay, so assuming that my input is connected, I want to say that my output is also connected. So let's prove this by contradiction. Suppose that the output is not connected. So just look at my output, look at the blue edges that I had. And if I'm saying it's not connected, suppose the output is not connected. So that means that I'm going to have at least two connected components, okay? So pick one of the connected components and put it here, let's call it C, and pick all of the rest and put it here. Let's call this V minus C. Okay. So these two are not connected because my output is not connected. But my original graph was connected. So it means that in my original graph, there were a bunch of edges going between C and V minus C. At least one, maybe more than one, but there's at least one edge, right? Because otherwise my original graph would also be disconnected. Okay, so my algorithm has gone over all of these edges in the order of weight, right? And these edges don't create cycles because I have a connected component here, and this connected component is actually a tree. I have a bunch of connected components here, so this V minus C is a forest. So adding one of these red edges would not create a cycle. So that means that my algorithm would add one of these edges, and it would particularly add the one with the smallest weight. So this contradiction shows that my output is definitely connected. So my algorithm is outputting a spanning tree. But now the question is, why is it a minimum spanning tree? Maybe someone can give me a different spanning tree, and maybe that spanning tree looks completely different. Maybe it doesn't have anything in common with my output, and maybe it has a smaller weight. Why can't that happen? So here's the thing. We prove. So let's say that T is the output of my algorithm. I know that it's a tree, so I call it T. And suppose that someone else has given me another tree, which is optimal. So let T star be a minimum spanning tree. Okay. I don't know how T star was obtained. Someone gave me T star. T star is an optimal tree. Now, I want to say that the weight of my tree T is less than or equal to the weight of T star. I want to prove this. And when I write something like this, when I talk about the weight of a graph instead of the weight of an edge, I just mean the sum of the weights of all the edges. So weight of T is just the sum of the weights of all the edges in T. I want to prove that the cost of the output of Kruskall's algorithm is less than or equal to the optimal cost, which is basically the same as saying it's optimal. Okay. So I have this graph T star. I have the graph T. What can I do about this? I want to somehow use the lemma that I proved at the beginning of this session, that adding one edge to a tree creates exactly one cycle. Okay. So here's what I'm going to say. Look at the tree T star. Let's say this is T star. Okay. So I'm showing T star in black. So I have this tree T star, and of course it's part of my original graph. And remember, I'm showing my original graph in red. So my original graph has a bunch of edges that are not in this tree. Maybe these edges exist in my original graph, right? And let's say I run my algorithm. So what does Kruskal's algorithm do? It keeps adding edges one by one, okay? So it adds the first edge, and let's say that the first edge is an edge that was also in T star. In this case, I just keep running the algorithm. So basically, I want to run my algorithm until it adds an edge that is not in this optimal minimum spanning tree, okay? So as long as my algorithm is making choices that are already in the optimal tree, I'm fine with that. I'm just going to let it go. So let's say my algorithm first adds this one, then adds this edge, then adds this edge, so on. This is all fine. Until at some point, my algorithm makes a decision that is not in T star, okay? If this never happens, if my algorithm always makes decisions that are in T star, then my T would be the same as T star, and I'm happy. My algorithm just created the same optimal MST, so there's nothing to prove there. But the interesting case is that at some point, my algorithm chooses an edge that was not in T star, okay? Let's call this edge E. Now I say, look at the graph T star plus E. Okay. So remember, what is T star? T star is a minimum spanning tree that someone else has given me. E is the first edge that my algorithm added, which was not in T star. So I'm just saying, take this T star and add the edge E. This is a tree, this is an edge. So we said that adding one edge to a tree creates exactly one cycle. So there is going to be exactly one cycle using blue and black edges here, right? What is that cycle? In this case, it's this cycle. Right. Now, remember that my solution T, the output of my algorithm, is a tree. So it cannot contain a cycle. So my solution does not contain everything in this cycle, right? But my solution does contain E. So that means that there is another edge in this cycle that is not in my solution, because my solution could not contain the entire cycle. Let's call that edge E prime. This is E prime. Okay. And actually, let me complete my solution. So let's say this was my whole graph. So this is the edge E prime. This is the edge that is in T star, but not in T. Okay. So now I claim that if I take T star and I add E, and then I remove E prime, that's a tree. Why is that the case? Well, T star was a tree, so T star plus E, which is like the union of the black and blue edges here, has exactly one cycle, and that's this cycle. And the way I chose E prime is part of that cycle. So if I remove E prime, that cycle is removed. But you can check that everything remains connected. So when I take T star, I add E, I remove E prime, that's a tree. Okay. And of course, you can also check that it's a spanning tree. It's touching every vertex. Okay. But the weight of this tree is less than or equal to the weight of the optimal tree T star. Because what am I doing? I'm taking the tree T star, I'm removing E prime, I'm adding E. But by definition, the way I chose E was the edge with the smallest possible weight among the remaining edges. So remember how I chose E? I said I just run my algorithm, and I say E is the first time that my algorithm chooses an edge that was not in T star. But my algorithm has sorted the edges by weight. And it always chooses the edge with the smallest weight. So the weight of E is less than or equal to the weight of E prime. Okay. If the weight of E is strictly less than the weight of E prime, then this one, this tree here, has a weight that is smaller than T star, and that's a contradiction, right? But we have another case, and the case is that the weights of E and E prime are exactly the same, right? That's possible. But if that's the case, well, I just change my minimum spanning tree from T star to this new tree, which just adds E and removes E prime. So I have a new minimum spanning tree now, and this new minimum spanning tree is closer to the output of my algorithm. So if you take the delta, the number of edges that are in one but not the other, now that one is closer to 0. So I can just repeat the same thing. I can repeat this until T star becomes equal to T. And this proves that T has to be a minimum spanning tree. Okay. So you see, sometimes the algorithm is much simpler than the proof of correctness of the algorithm. Great. Now, I want to also give you a different algorithm. And this is the algorithm of prim. So if you think about how HKUST works, basically I've sorted my edges and I keep adding edges one by one. So at every point in the algorithm, I have a bunch of separate connected components, right? So if you look at, for example, how this algorithm here works, I have this vertex and then I add this one, and then I will have like one connected component for each of these vertices, but these two are just their own connected component, and I keep adding, right? So the idea in prim is that instead of having a bunch of connected components and seeing which ones I can connect, what is like the cheapest edge that connects two different connected components, let's just keep one connected component and let's just expand it. Okay. So prim's algorithm says start with some vertex, whatever vertex you want. Let's say I start with vertex U, and take the cheapest edge that goes out of U. Okay. So I take, for example, let's say this edge. If there are many edges going out of U, so let's say I have U, I have a bunch of edges going out, and each of them has a weight, 1, 3, 5. Prim says, take the cheapest edge out. Okay. And then it says, now consider all the vertices that are covered by some edges of your tree so far. So you have U, and you maybe also now have another vertex, let's call that V. Now it says, look at all the edges that are going out of either U or V. And take the one with the cheapest weight. And keep doing this. So every time you have a bunch of blue vertices, which are vertices that are already colored, and you look at all the edges that are going from blue vertices to some other vertex. And among them, you pick the cheapest vertex. And you add that to your solution. And you keep doing this until you cover everything, until all vertices are covered. Okay. So we're going to claim that prim's algorithm also produces a minimum span. Okay. So in this case, let me just add some more edges. And let's say this is weight 1, this is weight 2, this is weight 5. I have a weight 1 here. So right now, these 3 are my blue vertices. I look at all the edges that are going out of the blue vertices, and I ask, what is the edge with the minimum weight? It's this one. Now, what is the outgoing edge with the minimum weight? It's this one, which has weight 2. Then I have this one, which has weight 1. Now, among all the edges that go out, what is the edge with the minimum weight? So I have 6. I don't count this 3 here because it goes from a blue vertex to another blue vertex. So I'm only looking at the edges that are going from blue vertices to vertices that are not yet covered, right? So I don't count this 3 here either, but I have this 5 here. So I can add this edge. And I would say this is my minimum spanning So you see that this is a completely different algorithm than Kruskal, because in Kruskal, I used to have many connected components, and every time I was asking, what is the cheapest edge that connects two connected components, right? But here, I'm just keeping one connected component, the blue vertices, and I'm always asking, what is the cheapest edge that adds one new vertex to my current connected component? Okay. First of all, why does this create a spanning tree? So I keep adding vertices one by one, right? And if my original graph is connected, I will eventually add all of my vertices. So whatever I'm creating is definitely spanning. It's definitely going to cover all the vertices. Why is it a tree? Because I always add edges between blue vertices and red vertices, right? So I never add two edges between two blue vertices that were already there. So I will never create a cycle. So it's going to be a tree. So it's a spanning tree. But now again, the question is, why is it a minimum spanning tree? And I'm going to leave that for you to prove, because the proof is very similar to the previous case. So you just have to find a way of finding an optimal tree, which is not necessarily created by your algorithm. And you look at the tree created by your algorithm, and you try to just change the optimal tree so that it becomes the tree that you have created without increasing its weight. Okay. So we've seen two algorithms now for finding minimum spanning trees. Now, the next topic I want to cover is that of directed graphs. We're going to kind of change to something totally different. And by the way, there are many really easy theorems on directed graphs in the book. Generally, I don't cover easy things. So you have to read the easy stuff on your own. So read the book. So what is a directed graph? A directed graph is basically a graph in which every edge has a direction. So my edges look like arrows now. And the idea is that if I have an edge like this, I can, let's say I have an edge from U to V. I can go from U to V, but I cannot come back from V to U. It's like a one-way street, okay? But if I want to give a formal definition, a directed graph is going to be of the form G, VE, where V is a set of vertices. So this is just like before. But now every edge is actually an ordered pair. So every edge E is of the form UV. So this is going to be an ordered pair. So the edge from U to V is different from the edge from V to U. Okay. So this is the only difference. Remember when I was defining a graph, originally this was just a set containing U and V, so the order did not matter, but now the order matters. Okay. Great. So when we were talking about undirected graphs or basic graphs, we talked about this concept of connected components, right? So what would be the equivalent of a connected component here? What would be the counterpart of a connected component here? If I have a graph, if I have a directed graph, one thing I can say is, let's just forget about the directions and let's look at the connected components of what we call the underlying graph. So the underlying graph is the graph where I have forgotten the directions. So if this is my original graph, my underlying graph would just be this, right? And as you see, the underlying graph is connected. But that's usually not very useful for us, because the idea of connectedness in undirected graphs was that if U and V were in the same connected component, I could go from U to V, and I could also go from V to U. right? But this is not the case here, right? So if I call this vertex, I don't know, A, I can go from V to A. I can take, I can go from U to A. I can take this path, right? But I cannot go from A to U, right? Or if I call this one B, I can go from U to V. I can go UVB, or I can directly go UB. But I cannot go back from B to U. So if I just look at the notion of connected components in the same way that I looked at it before, if I just say, ignore the directions and look at the connected components, it's not going to give me a lot of information. It's not going to be as useful as before. So we're going to define something else, and we're going to call this a strongly connected component. So here's the definition. I say that two vertices U and V are strongly connected if there is a path from U to V and a path from V to U. If there is, let's call it just a UV path and a VU path. By the way, what is a path now? Because we have directions, we have to kind of change the definition of paths. The definition of paths would be that basically every time I'm taking a step, I have to respect the direction of the edge. So when I talk of a path, I'm talking of a directed path. So I can go from U to V, but I cannot go from V to U in my path. And similarly, again, I have the definitions of walk, trail, all of those things. You can imagine that all of them just change a tiny bit, and the change in the definition is that you have to respect the direction of the edges. Okay. So basically, if I can walk from U to V, and I can also walk from V to U, then I say that U and V are strongly connected to each other. So based on this, I can define my strongly connected components. So a strongly connected component, or just SCC. I know why you're laughing. Is a maximal subset of vertices such that every two of them are strongly connected. Okay. If I give you any directed graph, you can divide it into a bunch of strongly connected components. So the strongly connected components partition your directed graph. Why is that the case? Because if you look at this one, if you look at the definition of strongly connected, this is a relation between pairs of vertices, and it's actually an equivalence relation. Right? You can check that it has all the properties of an equivalence relation. So if U is strongly connected to V, then V is strongly connected to U. Of course, every vertex is strongly connected to itself. And if U is strongly connected to V and V is strongly connected to W, what does that mean? There's a path from U to V, there's a path from V to U. There's a path from V to W, there's a path from W to V. So you can just connect these paths, and you can have a path from U to W and a path from W back to U. So it also has transitivity. So basically, this definition is defining a relationship between vertices that is an equivalence relation. And so hopefully you've seen this like high school discrete math, that every equivalence relation gives you a partitioning of the set. So every directed graph can be partitioned into a bunch of strongly connected components, in the same way that every undirected graph can be partitioned into a set of connected components. Okay. By the way, this is going to help you, this definition is going to help you with something in the last problem sets. But I am especially interested in a particular type of directed graph, and that's the directed graph in which every vertex is its own strongly connected component. Okay. So the counterpart of this in undirected graphs doesn't make much sense, because if you say I have an undirected graph and every vertex is its own connected component, you just have the empty graph. You have a graph with no edges, right? Every vertex is just on its own. But actually, when it comes to strongly connected components, and when it comes to directed graphs, I can say that I have a graph where every vertex is its own strongly connected component, and these will not be the empty graphs. So let me give you an example. Just look at this. In this graph, every edge is going from left to right, right? So no two vertices are strongly connected to each other, because if you take two vertices U and V, one of them is going to be to the right of the other one. So from the right one, you cannot go to the left. So every vertex here is its own strongly connected component. If I look at the set of strongly connected components, these are my strongly connected. Okay. Whereas like in a general graph, this will not be the case, right? So I can have something like this. What are my strongly connected components here? And actually, I can have edges like this as well, because these two are now different edges. This is not considered multiple edges. Okay. So this is going to be a strongly connected component, right? This part is a strongly connected component, and this vertex on its own is a strongly connected. So you see that in general, my strongly connected components can be big. But I really like the graphs in which every strongly connected component is just one vertex. And so I'm going to give these graphs a name. I'm going to call them DAGs. And DAG stands for directed acyclic graph. And just based on this name, you can imagine what my next theorem is going to be. So this is my theorem. I want to say, let G be a directed graph. G has no cycle. And when I'm talking of cycle here, I'm talking about directed cycles, because cycles have to respect the direction of the edges as well. So G has no cycle if and only if every vertex of G is its own strongly connected component. Okay. I have to add a very small point here. So let G be a directed graph without loops. Because I can have something like this, right? I can have a vertex that just has a loop to itself. That's considered a cycle. Right. But if I don't allow loops, then my graph G has no cycle if and only if every vertex is its own strongly connected component. So that's why I can say I like graphs where every vertex is its own strongly connected component, or I can just say I like acyclic graphs, graphs that don't have any cycle. Okay. Why are these two equivalent? So let's just prove it. Let's prove this side first. So assume that G has no cycles. Okay. I'm going to take two vertices, let's call them U and V, and I'm going to show that they cannot be in the same strongly connected components. This shows that every vertex has to be in a different strongly connected component than every other vertex. So every vertex will be its own strongly connected component. So let U and V be two different vertices. Now, just look at this. Look at U and look at V. What happens if they're in the same strongly connected components? It means that there is a path from U to V, and there is also a path from V to U. That's by definition, right? So I'm going to have a path from U to V. This might be a complicated path. And I'm going to have a path from V to U. This creates a cycle, right?
Yeah, maybe share the same.
Yes. So that's the thing. This creates a closed walk, right? So I can start at U, take this path, and then take this path and be back at U. This is a closed walk. We had a theorem for undirected graphs that said every closed walk contains a cycle. Now, if you go back and look at that theorem, you can actually prove it for directed graphs too. So every closed walk contains a cycle here as well. So given that I have a closed walk, I have a cycle. And the proof is exactly the same as the proof for undirected graphs, so I'm not going to do it again. Okay. So this is going to give me a closed walk. So I have a closed walk from U to U. So I have a cycle. Okay, but this is a contradiction because I was assuming G has no cycles. So when G has no cycles, every two vertices U and V have to be in different strongly connected components. So every vertex has to be its own strongly connected components because no two vertices can be together. Now the other side. So let's do this side, which means that we assume every vertex is its own strongly connected component. I want to prove that there is no cycle, right? Now I say, suppose there is a cycle. So let's just try to do proof by contradiction. So let C be a cycle. Now, first of all, C is not a loop because I said my graph does not have a loop. Okay, so it's a proper cycle. It's really a cycle that is touching a bunch of vertices. And again, remember we're in directed graphs, so this is a directed cycle. Okay. Let's just take two consecutive vertices in this cycle, any two. So let's say I take this vertex U here, and I take this vertex V. Okay. There is an edge from U to V. So that's a path from U to V. But there's also a path from V to U. Just take the rest of the cycle. So U and V have to be in the same strongly connected component. In general, all the vertices in this cycle have to be in the same strongly connected component. They don't even have to be right next to each other, right? So if I say that this is U and this is V, this part of the cycle is a path from U to V, and then this part is a path from V to U. So every two vertices in this cycle have to be in the same strongly connected component. But then I'm assuming every vertex is its own strongly connected component. So this cycle can have at most one vertex, but we also don't have loops, so this cycle cannot exist. Great. So we have now this concept of directed acyclic graphs. Now, why do I like directed acyclic graphs? Because you see what I did here? I said that I can put the vertices in an order from left to right such that all of the edges are going in the same direction. All of the edges are going right. I'm going to give this a name. I'm going to give this a nice name. Let's call it a topological ordering. Okay. So given a DAG, let's call it G, a topological ordering is just a permutation of vertices. Okay, but it's a permutation where every edge goes from left to right, such that every edge E in E, so let's say G is E. Every edge is of the form Pi to Pj, where I is less than J. Or I can say less than or equal to J so that I also allow loops. Okay. So for example, let me just copy this one. Let me put it here. So let's say my vertices had some number, maybe this one was vertex number 1, 2, 3, 4, 5. So a topological ordering would be something like this. I can have 4, and then I can have either 2 or 5, and then 1, and then 3. Right? So if I put the vertices in this order, all of the edges are going from left to right. And again, the topological ordering is not necessarily unique. So here I can also have 4, 5, 2, 1, 3. And you see that if I put the vertices in this order, all of the edges are also going from left to right. Right, so I have 4, 5, I have 4, 2, I have 4, 1, I have 5, 1, I have 2, 1, and I have 1, 3. And all of my edges are going from left to right. Okay. Great. Actually, instead of saying given a DAG, I can just say given a directed graph, because it's just a definition, right? So I'm just defining what a topological ordering would be. And then now I can give you another theorem. And this theorem is that a directed graph G is a DAG if and only if it has a topological ordering. Okay, and again, I don't like loops, so let's say a directed loopless. Loops are always just trouble for us. I don't want to consider loops. Okay, I have to prove two things. I have to prove that if I have a DAG, I can have a topological ordering, and I have to prove that if I have a topological ordering, then it's a DAG. Let's first do the second thing. Let's say that G has a topological ordering. Why is it a DAG when it has a topological ordering? So the definition of DAG was just that it doesn't have a cycle, right? But if I have a topological ordering, let's say this is my topological ordering, V1, V2, V3, so on, to Vn. And all of my edges are going from left to right. Can I have a cycle? No, because wherever I start, I'm always only going right. I will never come back left to the same place where I started. So if I have a topological ordering, I cannot have a cycle, which means my graph is a DAG. So one side of the theorem was pretty easy. Now the other side. Let's say my graph is a DAG. I want to prove that it has a topological ordering. Okay. To prove this, I'm going to just create a lemma first, and I'm going to come back to this later. Okay. So this is my lemma. when I was talking about undirected graphs, I could talk about the degree of a vertex. And the degree of a vertex was basically the number of edges that were coming out of this vertex, right? But now, when I'm talking about directed graphs, I can talk about in degree and out degree. So if I have a vertex U, I have a bunch of vertices coming in. And then I have a bunch of vertices going out. I can talk about the in degree, which is the number of, sorry, I don't know why I said vertices, edges. If I have this vertex U, I have a bunch of edges coming in and a bunch of edges going out. So I can talk about the in degree, which is the number of edges coming in. In this case, it's 3. Or I can talk about the out degree, which is the number of edges going out. In this case, this is 2, right? So this is the lemma that I want to prove. I want to prove that in a directed graph G, if the out degree of every vertex is at least 1, then there is a cycle. Why is this the case? Now, this is also going to have one of the easiest proofs you've seen in this course. I just say walk on the graph. Pick some vertex, pick your favorite vertex, U. Its out degree is at least 1. So there's at least 1 edge going out of it. If there are several edges, just pick whichever you like. Just pick an edge and go out. And keep doing the same thing. So when you get to this vertex, there's at least 1 edge going out. Pick one of the outgoing edges. And keep doing this. You cannot do this forever because your graph is finite. Remember, all the graphs in this course are finite. Right? So at some point, you're going to see a vertex that you've already seen before. And when you see a vertex that you've already seen before, that's a cycle. Okay? So easiest proof ever. Now, I can take the same lemma and I can, I can take the same lemma and instead of out degree, I can put in degree. And it still works. So if every vertex has in degree at least once, then there is a cycle. Why? Just do the same thing, but walk backwards. So pick a vertex, find an edge that is coming into this vertex, and go to the other end of that edge. And keep doing this. Keep walking backwards. You cannot do this forever. At some point, you're going to find an edge like this. And that's going to give you a cycle. Okay. Or another way of looking at this is that let's say I have my graph G. I don't know how copying here works. Why didn't it copy the D? D is there. Okay. So let's say I have this graph G. The in degree of every vertex is at least 1. So let's say that I just switch the direction of every edge. So every edge that was from U to V, I make it from V to U. Right? I'll get another graph in which the out degree of every vertex is at least 1. And I know that this new graph has a cycle, but a cycle in this new graph is already also a cycle in the previous graph. Because if you have a cycle and you just reverse the direction of every edge, you still have a cycle. Okay, so we have these lemmas. Let's come back to this part. So I'm going to call this star. Let's come back to star. So what was star? Remember, I was trying to prove this. I was trying to prove that a directed graph is a DAG if and only if it has a topological ordering. I've already proven that if it has a topological ordering, it's a DAG. Now I want to prove that if it's a DAG, it has a topological ordering. Okay, here's the thing. If my graph is a DAG, there is a vertex with in degree 0. Why? Because if every vertex has in degree at least 1, I have a cycle. And I'm assuming my graph is a DAG. So by that lemma, there is a vertex with n degree 0. Let's call this vertex U. I claim that I can put U at the beginning of my topological order. Why can I put U at the beginning? Because, well, there is no edge coming into U. So if I put U as the leftmost edge, as the leftmost vertex, all of the edges going out of U are by definition going to the right. Right? Okay, but now I remove U and I remove all of the edges going out of U from my graph. My graph was a DAG. Removing some vertices and edges is not going to magically create cycles. So it's going to remain a DAG. So in the remaining graph, I'm going to have another vertex that has in degree 0. I put that vertex next. And I keep doing this. And every time I'm putting only a vertex of in degree 0. So I'm sure that I'm not adding any edges that are going from right to left. All the edges are going from left to right. Okay. And I continue this until I add all of my vertices. So the way you can look at this, and actually you've already solved this problem several times in real life, is that imagine every vertex is a course that you have to take, and imagine that the edges are telling you what are the prerequisites of every course. So if you need to take all the courses, how would you do it? You will start with the course that has no prerequisites, and after you take it, you keep doing the same thing. Find a course such that you've already taken all the prerequisites and then take that. This is all this algorithm is doing. Okay. So a directed graph is a DAG if and only if it has a topological ordering. Now I'm going to show you a use case of this in some of the problems we've seen in the problem set. So here's what I call a DAG game. So a DAG game is just a game consisting of a DAG consisting of a loopless DAG. And let's say we have also two players. And let's say we also have a starting vertex. Okay. So the way this game plays is that we start at the vertex V0 and the players take turns. So player 1 plays first, and then player 2. In every turn, the player can choose one of the outgoing edges and can just take it. Okay. So in every turn, the player can choose an outgoing edge. Okay. And as we've seen in a bunch of games before, we say that a player loses if they cannot move. A player who cannot move loses. Okay. So let's say this is my DAG. Actually, yeah. Let's say this is my DAG. So I have some starting vertex. In this case, let's say my starting vertex is this one, V0. So I'm going to have two players. The first player chooses one of the edges going out. So let's say the first player chooses this one. And then we get to this vertex. and the second player has to choose an edge going out. In this case, there is only one choice, so the second player takes this one. Then the first player has to take an edge, let's say takes this one. And at this point, the second player takes, let's say, this edge. And then the first player cannot move, so the second player wins. Okay. So this process that I showed you is called a play of the game. Okay, so a play is basically just a path on the DAG. Right. Now, it gets more interesting if we assume that the players never make any mistakes. Okay, so assume that both players are just infinitely smart. Okay, both players are smart. Which means that they don't make any mistake, which, to be more exact, means that if they can win the game, they will not lose the game. Right? That's the definition of a mistake. The definition of a mistake is if you're in a state where you can win the game, but you somehow do something that loses you the game. So, and the definition of smartness is that you never make a mistake. Okay. So I want to prove some things. The first thing I want to prove is that the game always ends. So, or another way of talking about this is to say that every play is finite. I cannot play forever. Why does the game always end? Yeah, because there's no cycle. So I'm going to see every vertex at most once. If I have n vertices, I can have at most n steps, n minus 1 steps. So the game ends. Okay, but what's more interesting is that I can just tell you which vertices are winning vertices and which vertices are losing vertices. So I say a vertex is a winning vertex if when I start the game there, player 1 wins. And I say it's a losing vertex if when I start the game there, player 1 loses. Okay. So the second thing I want to say is that every vertex is either winning or losing. It's either a W or an F. Okay. Again, this is much older than the slang. So why is that the case? Let's try to prove this. First of all, we said that in every DAG, we're going to have at least one vertex in degree 0 and at least one vertex without degree 0 because of those two lemmas. Because if I don't have a vertex without degree 0, then definitely I'm going to have a cycle. But this is a DAG. Okay. So let's look at vertices without degree 0. Let's look at this vertex and this vertex. Are these L's or W's? They're L's, right? Because if the game starts here, and of course the game starts when it's the turn of player 1, player 1 cannot make any move, so player 1 immediately loses the game. Okay. But now let's look at the other vertices. So let's look at this vertex, for example. Is this a W or an M? Why? Yes. So if the game starts here, player 1 will just immediately go here, and this is an L vertex. So player 2 loses from there. So this is a W. This is also a W. So generally, if I have a vertex that has an edge to an L vertex, this one has to be a W. Because when I take my turn and I take that edge, my opponent will be in the L situation. So my opponent will lose. Okay. What can I say about this vertex? Yes, this is an L vertex. Because if the game starts here and I'm player 1, I have to take one of these two edges, right? But no matter which one I take, I'm going to give a W to my opponent. So my opponent is going to win. So I'm forced to call this one L. So the rule is very simple. if you have a successor, so a successor is a neighbor where you have an edge from your vertex to that vertex. If you have a successor that is L, then the current vertex will be W. If all the successors are W, the current vertex will be L. Okay, so based on this rule, this one is going to be W. This one, what is it going to be? This is also a W. Because if I'm here and the game starts, I have a choice. I can just go here and give my opponent an L, or I can go up and give my opponent a W. But that would be a mistake. And we assume that the players are smart, they don't make any mistakes. So the player will go to L. Okay. And so this one is an L, which means that all of these are W's, which means that this one is an L. So if I started my game here, player one will always lose. Okay, assuming that the two players. Okay, great. But now I have just two rules for assigning W or L to vertices. I'm saying if you have any L successor, you're a W. And if all of your successors are W's, you're an L, right? But the theorem is saying that every vertex is either W or L. Why is it that if I just apply these rules, every vertex will be labeled by either W or L? Maybe I have a vertex that never gets a label. I want you to prove that every vertex can get either W or L as its label if I have a DAG. So here's the thing. We had this theorem, right? We had the theorem that my graph G is a DAG if and only if it has a topological ordering. So I can just find the topological ordering of the vertices, and actually in this case, I already drew them topological ordering. And then we can start assigning L and W from right to left, right? Which is exactly what I did here as well. So every time that I want to assign a label to a vertex, I've already assigned labels to all the vertices to its right. But because this was a topological ordering, I know that all of the successors of this vertex are to its right. So I know which of the successors are W and which are L. Based on that, I can assign L or W to this vertex. And basically, you can do an inductive argument and you can say, I will eventually assign a label to every vertex. But this only works if we have a DAG. Because if I have a cycle, then using these two rules, I cannot assign anything to any of the vertices in the cycle. And actually, if I have a cycle, I will even have a problem with the first property. My game might not even end. I might just go through this cycle and maybe the two players just keep going around forever. Okay. Great. So this also solves a lot of the problems that we've had in the problem set, because basically all you have to do for a lot of the games we've had in the problem set is to assign a vertex to every possible state of the game, right? So the state of the game can be a bunch of numbers, whatever. For every state of the game, you just create one vertex and you put an edge if the player can convert this state to this state in one step. So all of the games that you've seen in the problem set are actually just very special cases of this game. And the same algorithm works for all. Okay, one final thing I want to cover here is the concept of rooted trees. And this is something that we will use very often. So you know what a tree is? A rooted tree is just a tree with one vertex chosen as the root. Okay, so a rooted tree is just a tree, let's call it T, vertex set V, H set E, in which one vertex is chosen as root. Some are in V, is chosen as root. So why would this be interesting? Let's say that I have a tree, and usually I draw my tree with the root at the top. So let's say this is my R, and this is my tree. Now, what I can do is that I can orient this tree. So I can give directions to the edges of the tree. And usually the way I orient it is from the root outwards. So I orient it like this. Okay. Sometimes I will do the opposite orientation, like towards the root, but normally it's away from the root. Okay. So when I'm talking about a rooted tree, I can think of it as an undirected graph, or I can think of it as a directed graph because I have this natural way of adding directions to the edges. But when I have this, then I will have some really nice terminology that we will use in a lot of algorithms. So I can talk about the children or the parent of a node, right? So if I have this node, all of the successors will be called children. So if this is U and this is V1, V2, V3, I would say that V1, V2, and V3 are children of U. And U is the parent of V2, and R is the parent of U, right? And then I can talk about grandchildren or grandparents, right? The same way. So if I have, I don't know, let's say T1, or T is not a good name. Let's say I have W1, W2 here. I have U1, U2 here. I have, I don't know, Z1, Z2. I can say that the grandparent of Z2 is U1. And I can say that the grandchildren of R are W1, W2, V1, V2, V3. And then I can also talk about ancestors. So the ancestors of Z1 would be W1, U1, and R. But usually I consider this vertex to be its own ancestor as well. So usually when I talk about ancestors, I say ancestors of Z1, I mean Z1, W1, U1, and R. Okay. I can, in the same way, talk about descendants. So the descendants of U1 are U1 itself, W1, W2, Z1, and Z2. So just think of it as kind of like a family tree. But yeah, the weird thing is that we always put the root at the top. I don't know why. In real trees, it's the opposite. But then you will have these vertices at the end, which have no outgoing edges, no children, and we call these leaves. But be careful about this because this is a little bit different than the definition of leaf that we had before. So in a rooted tree, when I say a vertex is a leaf, I mean it doesn't have any children. When I was talking about graphs in general, and when I was talking about trees without this definition of root, I was saying that a vertex is a leaf if it has degree 1. Now, these two things are not necessarily the same, because I can have a situation like this, where my root has degree 1, right? So if I was talking about this graph as just an undirected graph, or if I was talking about it as a tree, I would say that R is a leaf. But when I talk about it as a rooted tree, R is not a leaf. So whenever we're talking about leaf, be careful which definition of leaf we're using. In this case, we're using the definition that says if you don't have a child, you're a leaf.